Hello again, higher algebra students, back here with lesson 5 of unit 7, finding information graphically and being able to graph by hand, again, all under the umbrella of quadratics here. So we'll jump right in. So looking first of all at this, our parent function of y equals x squared. So again, y equals x squared, just as a reminder, the vertex is at that point 0, 0. 1 squared is 1, and negative 1 squared is 1, so those are two of the points. 2 squared is 4, negative 2 squared is 4, 3 squared is 9, negative 3 squared is 9, and so forth. So there again is our function, quadratic here of y equals x squared. And so when we look at, again, axis of symmetry, and looking at this without using any of necessarily our tools from Desmos or our tools from some of the shortcuts with each of the three types of formula between vertex, factored, and standard, just looking here and saying, okay, with this graph, I can tell that the axis of symmetry is right up the y-axis there. So our axis of symmetry is at x equals 0. Again, axis of symmetry is always x equals something. In this case, it's right with a 0. This does open up happy or up, and so it has a minimum instead of a maximum with the opening up. The y-intercept of this graph is at the point 0, 0. So that would be our y-intercept, which is also our x-intercept. So again, we've talked so much about quadratics with multiple x-intercepts and things like that, but our most basic one of all, the simple x squared, actually is the most straightforward, with just a couple 0, 0s there to represent our intercepts. So moving on, this here is a little more involved now. Okay, so we have an equation here in vertex form, and as we graph this, let's think about how we're going to graph this now. So the parent function of this is y equals x squared, and as we're looking at the format, so again, the format for vertex form is x minus h squared plus k. So we've got a plus 4 here, which means that h would have had to have been a negative 4 in order to make it a plus 4. So that just means that our vertex, the x value of our vertex, will be negative 4. Okay? The y value of our vertex, again here it's just plus k, and so because this is a minus 5, that means the y value of our vertex is a negative 5. So our vertex here at the point negative 4, negative 5, so we go again back 4, because that's an x of negative 4, and then down 5, because that's a y of negative 5 there. So here is our vertex. Okay? Now, the axis of symmetry will occur at that x, so that again, axis of symmetry is always x equals, and it's always the same as the x coordinate for the vertex. So that is x equals negative 4. Now the opening up or down, we have to think about what is that a term out in front, because technically I didn't write it there, but there is an a out front, and the a in this particular problem is 1, which of course means a is greater than 0, so that means it opens up. So this will be going uphill as we graph in either direction. Now, in terms of where these other points are, one thing that makes it really nice now is as we think about pattern of change, since a is 1, that means our typical 1, 3, 5 pattern of change is in play. Now, what that means for us when we graph it is we could certainly put the points into the equation to find more points to graph, but the 1, 3, 5 pattern of change just means that as we go over 1, we're going to go up 1 right out of the gate. Okay? Now, as we go over 1 more, we're going to go up 3. As we go over 1 more, we're going to go up 5. So this pattern of change actually allows us to graph this without having to put in 6 more points into our equation. Because as you can see here, I have an x equals negative 1, x equals negative 2, x equals negative 3, negative 5, negative 6, negative 7. So I could have put all of those in for x there in my equation. But the 1, 3, 5 just allows us to graph this without having to put those points in. And again, the 1, 3, 5 just means as you go over 1 in either direction, you're going to go up 1 the first time, then up 3 the next time, up 5 the third time. So our y-intercept here, as we continue going up, if we go up, in this case, up one more, over one more, we would be going up 7. So this, if we go over to here, we're going to go up 1, 2, 3, 4, 5, 6, 7. So you can see there, our y-intercept would be at the coordinate 0, 11. Again, we're typically just leaving that pattern of change at 1, 3, 5, but we had to get over one more unit in order to figure out what that y-intercept was. And this is a time where you could verify using Desmos that your answer is correct. The other way you could verify it is you could put 0 in for x in the equation, which would be 0 plus 4 squared minus 5. Well, that's 4 squared minus 5, or 16 minus 5, which is 11. So you can kind of verify the y-intercept there as well. Now the x-intercepts, the reason it says not yet here is because the x-intercepts are actually a little ugly on this one because they aren't whole number or integer values here. So we're going to hold off on the x-intercepts for now. But we do know that this function does have a minimum. Okay, and that minimum occurs at the vertex, which is the point -4, -5. So the minimum is actually at a y value of -5 on this particular problem. All right, let's continue on here. So we have another vertex form. Again, I'll just go really quickly here. There's a couple extra pieces on this one, but the vertex here, because it's a -2, that means that the x is a 2. With this as being a -1, that's actually a -1. And again, it's because the minus is built into the x side of this equation, but not built into the y side of this equation. If the vertex is 2, -1, then the axis of symmetry, not -2, has to be x equals 2, because again, that's just that value. This again, the a value up front, without having anything there, that would just be a 1. So a equals 1, which of course means a is greater than 0. So this opens up. And now the domain and range. Well, this is a form of the y equals x squared graph. Okay, so we're looking at that similar domain here of going from -infinity to infinity. But let's go ahead and graph it just to be able to provide the picture along with this. So the vertex is at 2, -1 right here. Similar to last slide, the pattern of change here, because a equals 1, the pattern of change would be 1, 3, 5 again. So that means as we go over 1, we go up 1. As we go over another one, we go up 3. And as we go over another one, we go up 5. So there's our 1, 3, 5. And again, there's our graph. So the domain here, there's nothing blocking it on the left. So the left side of the domain is -infinity. And there's nothing blocking it on the right. So the right side of the domain is +infinity. Again, domain is the x values. The range, there is a floor on this. Okay, the floor, of course, occurs right there. So the minimum of the range is at -1, which is at the vertex. And the maximum of the range is going to be infinity again, because this will go on forever. The y-intercept here, you can see, go on forever going up. And so that's why the max of the range is infinity, since the range is the y's. Now the y-intercept, you can see we do have a point right there that's signifying the y-intercept because it is right on the y-axis. And at that point, the x is 0, as it always is, and the y value is 3. So 0, 3 we have as our y-intercept here. Now, the x-intercepts, again, we're not going to jump into yet, even though in this case they actually are integer values at 1 and 3. But again, that doesn't always happen, so we'll leave that out for now. Now, lastly, where is this increasing and decreasing? Well, coming in from the left, it's decreasing, really starting at -infinity, and it stops decreasing at an x of 2. Okay, again, this is 2, -1, and again, increasing and decreasing, we're looking at x values here. So that decreases up until just before the x gets to 2, And then at this point right here, it's actually flat. It's not increasing or decreasing, so there's no bracket here. But then it starts to increase back up after 2 forever to infinity. So that would be our increasing and decreasing there. Continuing on with a slightly different version here where we have actually a negative out front. The negative out front, again, that's our A term. So what we're saying here is that A term, in this case, is actually a -1. Again, we don't necessarily write the 1, but the negative, that implies that there is a 1 there. And so the vertex here, again, as we look at just the regular vertex form, because it's minus, that means this would have been an x minus a -1 to get that to be a positive. So this is a -1. And then the y term is a 7 here, as that is, again, just a +7 at the end. So that's our vertex, which means our axis of symmetry is x equals -1, since it's just x equals whatever that x value is. Now, in terms of opening up or down, a equals -1 here, which of course means a is less than 0. So this opens down because the a term is negative. Now the y-intercept. So let's get over and graph this thing here. So we've got our vertex at the point -1, 7. So there's -1, 7. That's our vertex. Now because a equals -1, that means our normal pattern of change of 1, 3, 5 now gets multiplied by a -1. So our new pattern of change is now -1, -3, -5, since it gets multiplied by that leading a coefficient term there. So this is no longer our pattern of change. Here's our new pattern of change, which means as we go over 1, we go down 1. As we go over another one, we go down 3. And as we go over another one, we go down 5. And if we went over another one there, we'd be going down 7. So we've got this now frown of sorts quadratic, opening down, as we noted it would, right here. And now the y-intercept, we can see we do have a point right on the y-intercept there. I'll change colors to make it a little easier to see. So this is our y-intercept right there, which is at the point 0, 6. So our y-intercept here is 0, 6. And again, we won't worry about our x-intercepts yet, which are at non-integer values again. So there again is same sort of problem, but now we've got that -1 leading term. Moving on here, now as we get into standard form, the first thing we need to do is with the standard form is it's a little more difficult to find that vertex just straight up. So we do have to employ our -b over 2a formula. Again, that's going to give us the x of the vertex, and that we'll use for both standard and factored form because we'll convert factored form to standard before we find this. So we've got a little work to do here, and then that will lead us to the axis of symmetry and so on here. But the -b over 2a, so again, as we look at what the a and the b are in this formula, the b here would be -4, and the a in this particular problem is 1. And again, that's because this is a 1 technically here, and then we have the -4 right there. So that means that this formula here would be a -4 over 2a, and again, a in this particular problem is 1. So a -4 is 4. 2 times 1 is 2. So the x value of our vertex is 2. So the axis of symmetry, we do know to be x equals 2. Now, we do need to put that 2 back into the equation so that we can at least figure out what the y value for the vertex is for the sake of graphing this. So I put the 2 back in for x. So that's 2 squared minus 4 times 2, and then plus 3. 2 squared here is 4. Minus 4 times 2 is minus 8, and then plus 3. So 4 minus 8 is -4. -4 plus 3 is going to be a -1, which means our vertex in this particular problem is an x value of 2 and a y value of -1. So as we graph this, the first point I'm going to put in is this 2, -1 right here. Now from there, as far as opening up or down, well, we already established that the a term here is 1, which naturally means a is greater than 0. So this will open up as being happy. Now the pattern of change, again, is typically 1, 3, 5. And if a is equal to 1, then it just stays at 1, 3, 5, because then it's just 1, 3, 5 times 1, because you always multiply that pattern of change by the a value. Sorry, not by 1, but by the a value. So from here, I'm going to take from this point, go over 1, up 1 in each direction, then over 1, up 3 in each direction, then over 1 and up 5 in each direction. And there is our graph of this quadratic. Now the y-intercept, again, has a specific point here. The y-intercept occurs right there at the point 0, 3. In terms of the x-intercepts, again, we won't focus yet on how we get those, but just in this case, they happen to be points that are easily found here with a negative, or excuse me, a 1, 0 and a 3, 0. So we'll go ahead and put 1, 0 and 3, 0. But similar to what I had before on the previous slide, we won't worry about that yet because that would involve some factoring that we'll talk about soon, but just not yet. So again, being a version of the y equals x squared graph here, the domain is -infinity to infinity. The range, as we can see here, has a floor at -1. And it does continue to go on forever up. So it has a ceiling at infinity, or up to infinity there. And in increasing and decreasing, again, we're decreasing from the left up until, and again, this is all about x values here. So we're decreasing starting at -infinity, since that technically is where the domain is. And it decreases all the way up until we get an x that's 2. Again, that's a parenthesis and not a bracket, because we, at that point to -1, we aren't going up or down, so it's not considered part of the decreasing interval. Oh, sorry, I wrote that on the wrong one. So this would be here. And then on the increasing side, again, that doesn't start until just after 2, and it goes on to infinity. So the increasing is 2 to infinity, but not including 2. And the decreasing is -infinity up to 2. And again, not including 2, since that's the point where it's technically not going up or down. On here, the last form is this factored form. And the factored form, again, does have that leading a term, which in this case would be a 1 again. So a equals 1. So that's just something to note up front. The factored form is really good now for x-intercepts. Again, this is what, had we on the previous slide factored, we could get to this point to find those x-intercepts. But for right now, we'll just say when we're starting the factored form is all we're worried about. Now, in terms of finding the vertex here, there are a couple ways. The vertex is technically kind of halfway in between those x-intercepts, and so that is one way to do that. But the little more mathematical way is to actually get this to standard form. So, and that's foiling again. So that would be x squared. Outside is a -1x. Inside is a +5x. And last is a -5. So this here would be x squared plus 4x minus 5. And again, to find the vertex, then we're going to use that -b over 2a. And from this equation here. So -b over 2a, so b in this problem is 4, so that would be -4 over 2, and then a is a 1 out in front of that x, so that's a 1. So this is -4 over 2, or -2. So that would be the x coordinate for the vertex, which again should be about halfway between the x-intercepts, and we'll get to that here shortly. But now to get the y-coordinate for the vertex, we need to put that -2 back into the equation. So we'll put a -2 in for x there, plus 4 times -2 as we put it in for that x there, and then -5. -2 squared is 4. 4 times negative 2 is a negative 8, so that's actually minus 8, and then minus 5. So that would be 4 minus 8 is a negative 4. Negative 4 minus 5 is a negative 9. So our vertex here is actually at negative 2, negative 9 in this particular problem. Again, the axis of symmetry then is x equals negative 2, since it's just that value that goes into the axis of symmetry equation. And again, it's always x equals, since it's a vertical line on these quadratics that we're looking at. In terms of opening up or down, we noted already that a is equal to 1. That leading term here is equal to 1. That's up there. And that's greater than 0, so it does open up in this case. Now, in terms of the y and the x-intercepts, first of all, for the y-intercepts, let's go ahead and look at our pattern of change to make the graphing easier here. So pattern of change is typically 1, 3, 5. And again, since a is 1, we multiply that pattern of change by 1, which keeps it at 1, 3, 5. So from our point here, we go over 1 and up 1 in each direction, then over 1 and up 3 in each direction. There's our y-intercept. And then over 1 and up 5 in each direction. And there's our x-intercept. So as I draw this here, I have a couple things in play. So right here is the point 0, negative 5, and that would be my y-intercept, which again, in standard form, the y-intercept is that last term, which was a minus 5. So our y-intercept is the coordinate 0, negative 5. And then the x-intercepts, again, are the points that make each of these two equal to 0. And so we've got x minus 5 equals, x plus 5 equals 0, and x minus 1 equals 0. So what would the x's have to be? Well, we'd have to subtract 5 from both sides there, and we'd have to add 1 from both sides there. So that would mean that x would be at negative 5, so that we'd get negative 5, 0, and x would be at 1, so that would be 1, 0. And again, if we look at our drawing here, that would be supported. Here's the point negative 5, 0, and here's the point 1, 0. So again, the drawing and our rule here of what x makes this equal 0. So a negative 5 for x, so negative 5 plus 5 is 0. So that's this one. And then 1 minus 1 is 0. So that's that one. And again, the y value here will always be 0 because the x-intercept has a y coordinate of 0. So there is using the factored form to find these intercepts, x and y, again, opening up or down, vertex and axis of symmetry. We'll take one final look at that, but with a negative a term. So again, with this negative up front, that means that the a is negative 1 here. And that does create a little more work for the standard form. As we look at this standard form here, what we're going to do is we're going to distribute that negative out first. And so that gives us, actually I'll write it up here, that gives us a negative x plus 2. So you can see I just changed the sign of each of these, and then that's an x minus 4 still. So now when we FOIL this to get to standard form, we've got negative x times x, which is a negative x squared, outside, which is negative x times negative 4, so that's plus 4x, inside, which is 2 times x, so that's plus 2x, and then last, which is 2 times negative 4, or negative 8. So that there then would, as we combine like terms, would still be a negative x squared, but the two middle terms combine to be 6x's. Again, 2 apples and 4 apples is 6 apples, same thing here with x's. And then we have the minus 8. So to find the vertex, again, we're going to do this negative b over 2a, and the b here is a 6. The a is technically a negative 1, so we would have a x equals negative 6 over 2 times negative 1, since that was the a term, because that negative in front of the x squared made it a negative 1. And so that gives us negative 6 over negative 2, which means the vertex is at an x value of 3. Now again, to find the y value of the vertex, we're going to take that 3 and put it right in for x. So that gives us a negative, and then for x is 3 squared, plus 6 times 3, minus 8. Again, 3 squared is 9, but that's a negative out front, so that's negative 9, plus 18, minus 8. So negative 9 plus 18 is 9. 9 minus 8 is 1. So our vertex for this equation is at the point 3, 1. Okay? Which means our axis of symmetry here would be at x equals 3, because it's always the same as the x-coordinate of the vertex. Our a in this particular problem, we already said our a was negative 1. So naturally a is less than 0. So opening down, so we've got that this point here will be our max, and we'll look at the rest of this graph here now as we start to look at the intercepts. So with an a equaling negative 1, and again, our pattern of change typically being 1, 3, 5, but now we have to multiply that by a negative 1. So our pattern of change is negative 1, negative 3, negative 5. Again, opening down. So we've got our vertex here, and the negative 1 means as we go over 1, we're going to go down 1. As we go over another one, we're going to go down 3. As we go over another one, we're going to go down 5. And there is our, again, our x squared graph now after a couple of transformations here. Opening down, you can see the parabola there. And of course, the next question here is about the y-intercept, and the y-intercept we again found right there where it crossed right here, and that was at negative 8. Now keep in mind, we also already knew it was going to be at negative 8 because of the minus 8 in the standard form, which also highlights what the y-intercept will be. Now the x-intercept, again, for that we're going to go back to the original factored form equation, which had an x minus 2 equal, and again, if we set that equal to 0, and an x minus 4, if we set that equal to 0, that means when we solve for x for each of these, that our x-intercept should be at x equals 2 and x equals 4. Well, we can verify that here. Here's x equals 2. Here's x equals 4. So our x-intercepts are at 2, 0, and 4, 0. And again, the vertex was at 3, which is the average of 2 and 4. So that, again, allowed us to find that x-coordinate for the vertex as well, which allowed us to find that axis of symmetry. So you can see that the way that these all are kind of working together as we find each individual characteristic of this quadratic. The domain, again, this is a form of the x squared graph. You can see these arrows mean it's going to continue going on forever, and this will continue to get wider, and this will continue to get wider. It's never going to curl back in, so the domain will run from negative infinity to infinity. The range here, well, the minimum of the range, there is no floor. These are going to continue to go down. So the minimum of the range is negative infinity, but there is a ceiling here, and the ceiling occurs right here at a y value of 1, and the 1 is included. So this would be a 1 with a bracket on the right side of the range. Again, make sure you put the lower number on the left, the higher value on the right. In this case, the lower number is the concept of negative infinity, and the higher value is a concrete value of 1 for range as being the ceiling. Now, increasing and decreasing. So this is the going up to the top of the roller coaster and then back down. So we actually start out going up here. So we're increasing really from negative infinity, again, because we're increasing the whole way along here. And we stop increasing once our x value gets to 3. Again, this is the point 3, 1. That's our vertex, as we had noted earlier. Okay, and that 3 is not part of the increase because that's actually the very top of the roller coaster where we aren't going up or down yet. And so that goes, it starts at negative infinity, continues increasing until just right before 3. And then just after 3, it starts decreasing. And that goes on decreasing forever. So that decreases up to infinity. And And so that 0.3 is the only one not included from our original domain, because that 0.3 is the one spot where we aren't going up or down. Thank you, as always, for listening. And if you have questions, please ask.